4 to the right is
Yes.
Okay. Good.
We can get the full screen to go away.
Well, that was the demo thing.
Yes.
Let's see, file. What's that way down there?
No, that's the pointer.
Oh. This.
Yeah. Give me just a second, I'll get the webcam started.
She says just 1 second. Just tell me when.
Okay. Now people can see you.
Okay. This does work.
Yes, it should. Go ahead and give it a try.
Okay.
Yeah.
Okay, I'll see if I can move this along because I know I'm standing between you all and lunch, so that's important. This work builds on some work that we did previously measuring combinatorial properties of input test data with the idea of evaluating test quality. So what we've done now is use these methods and extend this to determining the size of test set relative to certain test goals.
I need you to stand close to this microphone or where?
Oh, close to. All right, I'd rather do that.
Okay.
Works better for me. Sorry. Got it. Okay, how's that? Better? All right, thank you. Okay, there's always a question of how many tests that we need, and what I'm going to be talking about today is not meant to necessarily replace the traditional measures, the traditional approaches, but we can bring more information to bear on these approaches. So one way that's always popular, of course, is run tests until we achieve a certain level of code coverage. Statement coverage, that's kind of weak. Branch coverage, that's better. MCDC coverage, modified condition decision coverage, is beyond branch coverage and much stronger. So, but the problem with that sort of approach is that often you don't know up front how many tests you need before you achieve your, for example, branch coverage until you start running it and measuring coverage. So one of the interesting things that's come out of this work is we're able to look at static analysis of the code and integrate that with the measures of combinatorial coverage, and that will tell us what the number of tests we need to achieve branch coverage in this case. And we'll get into that later. Another approach, looking at requirements, but then the question is, what defines a requirement and how thoroughly have we covered a requirement? So we can use this approach to look at whether the requirements are covered very thoroughly. An even better approach doing requirements-based tests, but using code coverage to ensure that the requirements-based tests have been strong. And that's the approach used in DA-178B, which probably everyone at NASA is familiar with because that's for avionics software. So I won't get into that. Statistical testing, where you assume that the distribution of faults and the discovery rate of faults follows a certain statistical distribution, and then you measure the detection of faults and determine when to stop testing based on that. Again, you have to assume certain statistical properties. We think that what we've done can improve and sharpen that analysis somewhat. That's an interesting research area. And the ever popular ad hoc, just test it thoroughly until we run out of budget. So what we can do is do a better job of that, we think. So can we use test data in estimating the number of tests that we need? Well, of course, there's some natural things. If we almost always want to make sure we cover all input test values, where we've at least one of every value, or at least one of every partition if we've got continuous valued variables and we've done some sort of equivalence classing. But we might want to cover all pairs of values, maybe three-way interactions, looking at that as well. But there's always a question of how far do we take that approach, and what does it bias if we do stronger interaction testing, looking at two-way combinations, three-way interactions, and so on. And then looking at whether the input data studies can help with structural coverage. And as I mentioned, that's an interesting thing that came out of this, is that we can do that, in fact. So what we want to do is really just use the characteristics, measurements of input test data in a different way to improve our ability to estimate the number of tests that are required to meet certain test goals, or when to stop testing, of course. So this is a little bit of background. Some of you have seen this before if you've been to the previous IV&V workshops, but I'll just do a few slides to just review it and basically explain what all this is about, and then we'll show how to use this background information. So interaction testing deals with the problems of looking at interaction failures within code. So what this graph is showing us right here is that single value faults account for somewhere in this range. These are different application domains. So somewhere between 15 to 60, 70% of failures in different application domains were caused by just a single value. So that's this x-axis down here. Two-way combinations accounted for a smaller percentage of failures, somewhere in this range. That's cumulative, so that's two-way or one-way faults. And three-way interactions accounted for an even smaller set, and out to five- and six-way interactions. So what we mean by interactions is that line that's highlighted right there. If we have a failure that occurs whenever pressure is less than 10, volume is greater than some number, velocity is equal to some number. So three variables, three conditions there. So that's what we refer to as a three-way interaction, five- and six-way interactions, and so on, analogous to that. So what we've done is refer to this as the interaction rule. Most failures are triggered by one or two parameters, and progressively fewer very rapidly tapering off by three or more parameters. So if we test all of these combinations, then we can do very strong testing. So there are efficient ways of generating a matrix that covers all, say, two-way interactions, three-way up to six-way interactions. So we can generate matrix that will cover those efficiently. And this just gives you an expression, but the number of tests involved is proportional to that. But the key point is that you can do this even on very large problems because it's only logarithmic with the number of variables, which is n. So that's a nice property. Now, the coverage measurement that is sort of the basis for this, this fault coverage, which we're going to talk about in a minute, is what we've got here. So let's say we have 4 tests on the left-hand side there, 1, 2, 3, and 4. And each of those tests has 4 different variables, and they are Boolean. So we've got 0s or 1s. So the question is, what sort of coverage, combination coverage do we have for these 4 tests on the left? So if we look at AB, we have 3 two-way combinations covered for the pair of variables A and B. We've got 0, 0, 0, 1, and 1, 0. So we've covered 75% of the 4 possible two-way combinations of variable A and B. And we do that for every pair. And we come out with this sort of a distribution right over here. So we've only achieved full 100% all 4 combinations for a third of these values, a third of these pairs, these 2 down here, and we've covered at least 50% for everything. So we can graph this. What this is showing us, as I mentioned, we covered at least 50% for everything. So there's that one that was covered at the 50% level, and these 3 at the 75% level. This is the level of coverage in the y-axis. So that is basically a graph of the table that we put up before. And when we add tests, then we can improve this. So if we add a test, then this refers to 100% coverage. So we've added an additional combination. Now we've got 3 of the 6 pairs that have covered all 4 two-way values, 0, 0, 0, 1, 1, 0, and 1, 1. So we've added a test, and that improved that coverage. And if we add another test, then we've got more full coverage. We've also, we've brought our coverage of 3 out of the 4 possibilities up to this level, up to 75%, and add another test that gives us a full array covering all possible two-way combinations for this set of tests. So that's a very small example. We can do this for very, very large problems. So even though this was only just a few variables, we can do it for hundreds of variables. And putting all that together, this is a tool that lets you diagram this process. Right here, the red line is two-way combinations. So this is showing us, this is for real software. This is spacecraft software, about 7,500 tests. And looking at the coverage of that, you might have seen this before. So the red line says that we've covered this proportion in here, a very high proportion of the two-way combinations. The blue line is three-way combinations, so we've covered a fairly high proportion of that. But the key point for the what I'm going to be talking about today is that when we cover two-way combinations, we also get a very high percentage of three-way combinations. Four-way was somewhere out here, 5- and 6-way, and so on. So we get additional coverage for the T-way combinations that we cover. So if we cover all two-way combinations, then we're going to get relatively high proportion of three-way combinations, reasonable high proportion of four-way combinations, and so on. And this is something that will be useful later in the in combining this with structural analysis for the test. And we'll go back, we'll come into that in just a little while. But the key point here is that this minimum value, as I pointed out before, we've covered everything to the 50% level. Now, something new, which is the rest of this. So fault coverage, if we wanted to look at faults that occur in systems, the graphs that I put up before showed how faults occur in different application domains, the distribution of faults in different application domains. And what we can do is combine that distribution with the coverage of combinations. So let's say we do a two-way array. We've covered all two-way combinations of variable values And we have a fault distribution that looks like this on the left here. So the fault distribution, we can think of that as that the graph that we put up before, where we've covered about 60% of single value faults, and 25% of the faults that occur are two-way combinations, and so on. So if you graph that cumulatively, you get 60% for one-way, 85% for one or two-way, and so on up. So then we want to look at the coverage of combinations, and we've covered 100% of one and two-way combinations. So that means we should expect to get all the single value faults, and we should also get all the two-way faults, which account for 25% of our failures. But we've only covered 80%, and if we cover full two-way faults, we're going to get a very high percentage of three-way combinations. It's not going to be exactly 80. I made that up here for easy calculation, but it'll be relatively high in that range. So we've covered 80% of those, and 10% of the naturally occurring faults are three-way. So we could expect to get 80% of those three-way faults. We are not guaranteed to get 80% because the 80% that we've covered may not be the ones where the faults occur. But on average, it's a reasonably good way to estimate it. If we add all that up, then we can get roughly 95% for this made-up example here. So why does all this matter? Well, on the left, we have the distribution of faults in different application domains. But then when we look at the coverage of combinations and combine that with the fault distribution, then we have fault coverage, which is what we've just calculated, which is on the right here. And the two things are important here is that the fault coverage is probably going to be better than what you would expect from looking at the distribution. If we look at our distribution on the left, and we see that about 70% of the problems are caused by one or two-way interactions, and we do a full two-way array, then we might say, well, we'll get at least 70% of the faults. But empirically, what happens when you do this sort of testing, you get much better than that. And so that is to be expected, and that lines up with the fault coverage that you see on the right. And that's the sort of thing that you see when you do this kind of testing. So this is a way of just doing a simple calculation of what sort of coverage you can get. Now, the other interesting thing in this is looking at static analysis of code and seeing how that interacts with combinatorial combinatorial coverage that we just talked about. So let's say we had a piece of code that looks like this. If a certain condition is true, then we take the red branch. Otherwise, we take the green branch. And our input model, we partitioned the inputs into 5 of each. So there are 25 possible pairs. And 9 of those 25 go to the red branch. 16 of those 25 go to the green branch. So out of these, the smallest of these is the 9 over 25. So we're going to take a look at that. And that's what we're going to call B, which is the minimum number of branches taking one way or the other. So that's the smallest in this set here. So there's a fairly natural way that fits together with combinatorial coverage. So what we talked about before, let's say if we covered all two-way combinations, then of course we know we're going to get all branches that depend on two variables. But what this condition tells us is that we don't really need to cover all two-way combinations because, of course, not too surprising, if we've got 9 going one way, 16 going the other way, then if we have 17 two-way combinations covered, then we're guaranteed to get both of those branches because there's only 16 going one way. If we've covered 17, then that means that we've picked up something in the 9 that go the other way. So we're going to get full branch coverage for this example if we cover that percentage. And so this little condition just captures that. And the tools measure the coverage, and we can combine that with static analysis of the code to determine if we're going to get branch coverage out of a set of tests. So that's nice, but why is it important? Well, one interesting thing is that covering arrays, covering all 2, 3, 4-way combinations and so on are very useful, but they can be expensive and fairly large. Let's say we have 10 variables with 5 values each. So 309 tests will cover all 2-way combinations of those, but if branch coverage is our goal, then we don't need anywhere near that. We can do, in this case, 225 tests, which is a big savings. So if the tests are expensive, then this tells us how many tests we need to get full branch coverage, and it can be far fewer than doing the full covering array of all possible 2-way combinations. So it's not as good as the full 2-way array, but it can still be very strong. So what does this mean for testing? Well, one thing is uncertainty. So when we do testing, of course, we need to know some range of the uncertainty in our estimates of how many faults we're going to detect and our ability to detect faults. Thinking back to the graph that we saw before, when we get up to 4-way combinations, there's a very small range of uncertainty. So that tells us, doing this sort of analysis, what sort of uncertainty we should expect with a certain number of tests. Number of values per variables, didn't have time to get into that, but the more values per variable, the more uncertainty you're going to have. Not too surprising, but we can quantify this. The branch coverage condition we just talked about, where we can show that we need, how many tests we need to get branch coverage, and it can be smaller than a full covering array. And then also we can do this in looking at requirement specification. A reasonable requirement for testing would be to say cover all 2-way combinations or all 3-way combinations. And this is a way of coupling that with an estimate of the fault detection that we could expect. And those are some ways we can use this to determine test set size. Now, factors in determining the size, we look at the fault distribution. Now, we can use historical fault distributions, as I've put up here, or of course we can do some sensitivity analysis by hypothesizing the fault distributions. What's the worst case fault distribution? Then we can compute the ability to detect those faults using the coverage, the combinatorial coverage that we have. So if we have a certain goal in our testing, we can look at how additional tests, how adding tests will increase the fault coverage and therefore our ability to provide assurance. And we can do some range of uncertainty which we deem reasonable, and we can measure that. So that's the important point here, is that we're able to measure this in a sound way. So looking at what sorts of fault coverage we might expect with the 2 to 5-way tests, as I mentioned, we can do some hypothesized fault distributions. So if we have sort of a typical system, we might see something like this. As you expect, when you test systems, you find all the single value faults quickly. The 2-way combinations are harder to find. The faults that occur only when 2 factors are true, those are harder to find. The really hard ones involve 3 or 4 factors and so on. So if we have a system right out of the box, we might think that its distribution of faults could be somewhere in the range of those that we see on the left. Whereas if we have a very well-tested system and we've covered all 1 and 2-way combinations, then we found all of those faults. There are 0 faults occurring that are 1 or 2-way. And in the red one, 0 faults occurring in 1, 2, or 3-way combinations. So then those lines on the right-hand side give us some estimate of what sorts of fault detection we should expect for a very well-tested system. So we can quantify this again. This is just taking a better look at this. So the greater uncertainty and lower level of assurance is going to be the two-way combinations and three-way combinations. And when we get up to four-way combinations, going off to the right there, circled in green, we have better assurance because we're getting higher fault detection and also less uncertainty. So that's a key point. So in summary, we can use combinatorial methods to give us much better estimates of fault detection capability. We can evaluate the effects of distribution changes in distributions and do some reasonably good sensitivity analysis. And another really interesting thing is that we've established a relationship between static combinatorial coverage and dynamic coverage of the code in statement or branch coverage. So questions? This is a website that will explain this, and we've got papers that look at this in much more detail. Okay.
Quick comment. I guess
Yeah.
what I liked about this is you could go in at any level that's acceptable to you and the client.
Yes, exactly.
Yeah.
Yeah, and you can agree on something based on your budget, and if you say that the budget is such and such, then you can say, well, within certain ranges, we can expect this sort of result.
Thank you.
Yeah. And it's reasonably defensible and quantifiable. Thanks.
Thank you, Rick. There are no other questions online.